So I'm Max Tegmark, and it's a great pleasure of mine to get to introduce Surya Ganguli to kick off our fall colloquium series here at IAIFI at MIT and neighboring universities where physics meets AI. Surya is a really awesome speaker, as you're going to see. And he got an early start on his career. You managed to graduate, Surya, from high school already at the ripe old age of 16, I gather, and then had the great wisdom to come to MIT for undergrad. And after a stint in Berkeley and other places, Surya has been at Stanford since 2012 now, doing a lot of interesting things. Among less known famous things I can share with you about Surya is that he actually grew up on a ship and once had a very thick Scottish accent. So I'm really counting on at least the first sentence or two in your colloquium being in Scottish here. So one final thing I want to add before we let you start, Surya, is just on a very personal note that you might not realize, Surya, how much influence you've had on my own career, because 5 years ago, I was progressively getting more and more excited about working in AI, but it was kind of scary, this idea of going into a whole new field and wondering whether that was even possible at my career stage. And seeing a talk by you actually really made it click for me. It made me realize, hey, there is actually a lot of stuff that we physicists with our tools can contribute to machine learning. So thank you so much for helping me see the light, Surya, and can't wait to hear you tell us about weaving together machine learning, theoretical physics, and neuroscience through mathematics. Take it away.
Thanks, Max. I didn't know that story, actually. That's great to hear. And as always, it's super fun to hang out with you all over the world. So it's too bad I can't be back at MIT right now. I always love coming back there. As Max mentioned, I was an undergrad there, so I have very, very fond memories of being an undergrad there. So yeah, I'm sorry that I forgot to change the title of my talk, but anyways, the content has changed. So in any case, so what do I do and what do I do with my lab? A lot of the times we're actually working on a bunch of neuroscience problems, right? Like how do flies see, how do mice navigate, how do monkeys reach, and stuff like that. And we're trying to understand how biological neural circuits do this. But so generally we like to understand how the brain works, but there's actually a lot of related problems to that problem, right? Which is and this motivates sort of an alliance between theoretical neuroscience, machine learning, and physics, and in multiple ways. Here's one way, right? So we'd like to, for example, understand how a brain circuit works, but what does that really mean? Well, we'd like to understand how the connectivity and dynamics of neural circuits give rise to behavior. And also learning is important. We'd like to understand how neural activity and synaptic learning rules conspire to self-organize useful connectivity that subserves behavior. But interestingly now, the field of machine learning has generated lots of neural networks that accomplish interesting functions that we know of no other way of accomplishing using any other artificial system at the moment, right? We know everything about these systems from an experimental perspective. We know their connectivity, their dynamics, their learning rule, their developmental experience, yet we don't have a meaningful understanding of how they learn and work. And moreover, can we even go beyond that to exploit novel physics to implement these successful neuromorphic computing schemes at even lower power and higher speed, right? So addressing some of these questions really brings into bear the power of complex systems analysis developed in other fields that have been, designed to attack complexity in their own domains, things like statistical mechanics and other aspects of applied mathematics. So we wrote a current opinion on this a while ago. And actually, as a result, we've actually spent a lot of time working not only on biological neural networks, but also on artificial neural networks and more generally machine learning in sort of an attempt to develop a unified theory of how both biological and artificial networks might work. I mean, that's the long-term goal. We're not there yet. So here's some examples. And actually, in the process of really trying to attain a conceptual, quantitative, mathematical understanding of how these neural networks work, we actually realized we could use a lot of tools from physics and applied math. including non-equilibrium stat mech, dynamic mean field theory, the statistical mechanics of random landscapes, Riemannian geometry, random matrix theory, also free probability theory, and so forth. And if you're interested in sort of a review of some of this work, as well as other people's work, we recently wrote an annual reviews of condensed matter physics, trying to sort of put some order in this field. And so we talked about how we can think about physics approaches to analyzing machine learning. What can deep neural networks say that shallow networks cannot? What does the error landscape of neural networks look like? How do signals propagate through deep networks? How do deep networks generalize? And how can we teach them to imagine new things that are not in the training set? So that these deep generative models. So if you're interested, this might be an interesting starting point. Okay, I can't possibly tell you about all of this work. So today I just kind of chose sort of 3 vignettes, right? We're going to start relatively simple, and we're just to talk about something that you might think we know everything about, which is just how do you do regression in high dimensions? And it turns out there's even new stuff to be learned here using ideas from physics. In particular, what's the optimal way to do regression in high dimensions? And that's this couple of papers. True to my kind of neuroscience roots, I wanted to just tell you a fun story about deriving the structure of your retina and more generally the retina of any primate, again, by from first principles, from understanding the statistical structure of natural movies and showing that if you design neural networks that optimally process natural movies, then out pops in detail the structure of your retina and also the retina of monkeys, which are not that different from our retinas. Okay, so that's this paper here. And then because of this particular center, I decided to spend a bulk of time focusing on so-called quantum neuromorphic computing with atoms and photons, where we try to implement neural algorithms using the intrinsic dynamics of interacting atoms and photons. And we get a slight twist on the types of stuff that we see in classical neuromorphic computing. Okay, so let's get started. So high-dimensional data analysis is a major sort of frontier of statistics at the moment, driven by revolutions in the way that we collect data, our ability to do high-throughput data collection. So what is this modern high-dimensional statistics? Well, if we think about classical statistics, if we let P be the dimensionality of our data, i.e. for each data point, the number of simultaneous scalar measurements you make, and we let N be the number of data points, in classical statistics, what often happens is we carefully choose ahead of time which variables we care about. So the number of simultaneous measurements we make is usually pretty small, but we take many measurements. So this measurement density, which is the ratio, I hope people can see my cursor, but let me know if you can. This measurement density, the ratio of the number of data points to dimensions, is going off to infinity. So this is a cartoon picture of low dimensional data. It's easy to find regression lines. It's easy to do clustering. It's easy to find patterns. Okay, but of course now we take data first and ask questions later, right? We can record thousands of neurons in an animal. We can record gene expression patterns of thousands of genes in individual cells, but we don't know ahead of time whether these neurons and genes are relevant to answering the question we care about or relevant to predicting a particular disease state versus not, right? So what's happening here is the dimensionality of our data is becoming large. The number of data points is also becoming large, but their ratio is order 1. The measurement density is order 1. It's not infinite. So a cartoon picture of this data would be like 3 data points in a 3-dimensional space, right? It's hard to imagine how you can do accurate data analysis in the setting without potentially hallucinating structure in your data that's not there, right? Well, there's a beautiful connection between machine learning and data analysis that you can see right here, right? So the goal of machine learning is to learn the statistical parameters of a model by maximizing the log likelihood of the data over the set of parameters, right? So this is maximum likelihood estimation, for example, okay? If we think about energy as the minus log probability of the data given the parameters of your model, right? then this maximum likelihood estimation problem corresponds to a statistical mechanics problem where the data is fixed. You're not allowed to optimize over the data unless you're doing something like active learning, because you've taken the data already. So the data plays the role of quenched disorder in the statistical mechanical problem. And the parameters of your statistical model, the things over which you're minimizing the energy, they correspond to thermal degrees of freedom that are allowed to adjust themselves, right? And we're looking for zero temperature minima of this energy function, right? And so we can, in this high dimensional limit, by recasting statistics as a problem in the statistical mechanics of quenched disorder, we can answer all sorts of questions about how well we imagine, for example, regression in high dimension should behave, right? So we've spent some time working on this problem. Here's a sequence of papers, but I'm going to focus on a very specific problem. Oh, by the way, another review article, if you're interested, is this. We wrote a while ago a review article in Statistical Mechanics of Complex Neural Systems, High Dimensional Data, where we use techniques from condensed matter physics, basically the replica method, to describe in a unified manner neural networks, learning, random matrix theory, random projections, compressed sensing, and so forth. So if you're familiar with these techniques, then this might be a good place to start delving into these topics. Okay, so what's the problem that we're going to look at today? So let's talk about, so what we want to do is we want to ask, what's the optimal way to do regression in high dimensions, right? So if we start from the right, we're going to be doing theory. So we're going to be assuming that we have a generative model for the data, right? So we're going to be assuming that there's some unknown p-dimensional signal S0, okay? It's a p-dimensional vector. We're going to assume that the components, the p components of this vector, are drawn IID from a signal distribution, p sub s. So this is a probability distribution over a scalar value. It doesn't need to be Gaussian. So this is an arbitrary probability distribution for now. Okay. We're going to assume that we get to take n measurements of this p-dimensional signal, but our measurements are corrupted by noise. Okay, a critical parameter is the measurement density, the ratio of the number of measurements to the number of dimensions or number of unknowns. And what does each measurement look like? Well, we can imagine this unknown signal as a set of weight vectors of an unknown, for example, just linear perceptron or something. So we have this unknown signal S0. We get to probe it with inputs. Okay, each input generates an output through this process here. You take S0, you take the dot product with the input, and you corrupt it with noise. And that's your measurement Y sub mu, okay? So you could think of this as a single neuron with unknown synaptic weight vectors. You feed it inputs, you measure the outputs, and you're trying to reconstruct the unknown weight vector, S0, okay? Of course, you don't have access to S0. You only have access to the measurement data, the inputs and outputs to the system, and you'd like to construct an estimate S hat. And you'd like it to be as close as possible to the true ground truth signal S0. Okay, so you get the x's and mu's, so you have to come up with an estimation algorithm. So you have the x's and mu's, the x's and y's. These are your inputs and outputs of the system. And you have to construct an estimate S hat. And we often do it using a particular loss function rho and a particular regularizer sigma, okay? The loss function rho, so what you often do is you optimize over the space of all possible unknown signals, and you try to find the one that that comes as close as possible to making the right predictions in your training data. So rho is a loss function that penalizes deviations between the output that you got and the predicted output you'd get if your unknown signal were S. Okay, so this encourages staying true to the measurements, staying close to the measurements. You might have some prior information like knowledge of this P sub S, and you might try to use that to construct a regularizer to promote certain configurations S. Okay, now in this high dimensional setting where P and N go to infinity, but their ratio is order 1, we can measure, for example, how well we estimate S0 by the squared error, the Euclidean distance between squared Euclidean distance between S hat and S0, right? The generalization error, i.e. your prediction performance on held out data, is monotonically related to this quantity. So this is going to be, this is our performance measure. This is going to be a function of the measurement density, the loss function, the regularizer, the noise distribution, and the signal distribution. Okay, and so the ultimate question we'd like to ask is, for a given signal distribution and noise distribution and measurement density, what is the best loss function rho and regularizer sigma? Okay. All right, now we first note that almost everything that we do in regression is a special case of this much more general formulation. So for example, least squares regression corresponds to a squared loss and no regularizer. Maximum likelihood estimation turns out to correspond to something where the loss function is a minus log probability of the noise distribution, okay, and no regularizer. Ridge regression is squared loss and squared regularizer. Lasso is this, where you use an L1 penalty. Elastic net is another one. Map estimation, maximum a posteriori inference, is one where the loss is the minus log probability of the noise distribution, and the regularizer is the minus log probability of the signal distribution. So minimizing the regularizer is maximizing the prior probability, okay? So anyways, a lot of the algorithms that we know and love are special cases of this, all right? So, but this leads to an embarrassment of riches. Out of all of these algorithms, which one is the best? The answer could be none of the above, of course, and if so, we'd like to know that, okay? All right, so we answered these questions, and again, the techniques that we used were, this quantity is like an energy function, S is like thermal degrees of freedom, X and Y are quench disorder, and we write down a Gibbs distribution over S with this quench disorder, and we send the temperature to 0 so that this Gibbs distribution will concentrate on S hat, and we can analytically compute Q sub S as a function of all of these things. Okay, so there's lots of pages of calculation behind that, but I'm going to skip all of that and tell you the final answer, which is intuitive. Okay, so of course, by the way, okay, so sorry, so one minor trick. So we can compute the error as a function of rho and sigma. Then with this analytic expression, we can do variational calculus. At fixed alpha, p epsilon, and p sub s, we can find what's the optimal rho and sigma. So that's how we get the optimal rho and sigma. So that's basically, in a nutshell, the method. Okay, the details are all in the paper. All right. So here's an example. Let's say the signal distribution were the noise distribution were Laplacian, and the signal distribution were Laplacian. Okay. Then what is the optimal loss function and regularizer? Well, it actually depends on the measurement density. It depends on how much data you have. If you have lots and lots of data, you have high measurement density, it turns out map estimation is the best thing to do. So the loss would be the minus log probability of the noise. So that's this absolute value function. And the regularizer is the minus log probability of the signal distribution. So that's this absolute value function. But it turns out as you reduce the measurement density, as you have less and less data, you can do better by nonlinearly smoothing this map estimator, this map loss and regularizer. So you get a slightly smoothed version. And then if you have very, very little measurement density, this nonlinear smoothing, what it does is it turns this function into a quadratic function, just a quadratic loss and a quadratic regularizer, which corresponds to ridge regression. Okay. There's a technical assumption we need on the signal and noise distributions in order to prove this result, which is that they're log concave. Okay. So the logarithm of this thing is concave, or alternatively, the minus of it is minus log probability is convex. So we get a convex energy function for the optimal value. This turns out to be tantamount to a replica symmetric assumption in our analysis of the condensed matter system with quench disorder. Okay, so for any log concave signal and noise, the optimal loss and regularizer are nonlinearly smooth versions of map, where the smoothing increases as the measurement density decreases. Map is optimal at high measurement density. Ridge regression is optimal at low measurement density, independent of the signal and noise, as long as they're log concave, right? So all these Bayesian people who tell you better care about the signal and noise distribution, that may be true in low dimensions, but it's not true in high dimensions. In high dimensions, as long as you satisfy this technical constraint, you can ignore the signal and noise distribution and just do ridge regression, and you'll actually be performing optimally, which is kind of a surprising result. We can also show that no inference algorithm can outperform our optimal algorithm in this setting. We show the gap between this and computing the posterior mean is 0. essentially. Okay, so just to show agreement between theory and experiment, right? So this is the same Laplacian example. This is the measurement density. This is the normalized error, or the fraction of unexplained variance between that S hat has about S0, right? So 1 is bad, 0 is good. Okay, the red is map estimation. The error bars are from numerical simulations of modest sized problems, sort of N and P are around 200 or so. The solid curve is theory, right? And there's a nice match between theory and experiment. Blue is ridge regression, same theory and experiment, there's a nice match. Black is our optimal algorithm. And as you can see, at high measurement density, map estimation does better than ridge, right? And it will eventually come close to optimal. At low measurement density, ridge does better than map, right? Despite having no knowledge of the signal and noise distribution in it. And it approaches the optimal algorithm. And switching the algorithm can have a big effect. So if you look at this horizontal thing, right? For a criterion level of performance, you can get the same level of performance compared to map by switching to the optimal algorithm and reducing the amount of data you have by, about 30 to 40%. So you can achieve a 30 to 40% reduction in error just by changing the algorithm. Okay, so if you're interested in the details of this, they're all in these couple of papers. But this is a nice example, I think, of how physics can be used not only to understand machine learning, but to come up with better machine learning. Right? Okay, so then, again, I couldn't resist talking about like biological circuits, but I chose just one example because it illustrates again how physical thinking, in the sense of optimization, can be used to deduce ab initio the properties of one of the most important steps of vision, the first steps of vision, how our retina captures the visual world. Okay, and that's this paper here. So let's see. So here's a crash course on the retina. All right. So the retina is actually a one hidden layer neural circuit, right? The first layer are the photoreceptors. These are very sensitive objects that, or very sensitive receptors that in the dark are so sensitive that they can detect individual photons, right? In the light, of course, they adapt and become less sensitive. There's a layer of bipolar cells and amacrine cells and horizontal cells. And then finally, there's these ganglion cells, okay? You all have about 1 million ganglion cells in your retina, and everything you know about the visual world comes from those 1 million ganglion cells. Okay, how do we model these systems? How do we model the input-output mapping from visual stimulus to firing rate of a ganglion cell? We often just, to a first order approximation, we model it using a spatiotemporal filter, right? Followed by a rectifying nonlinearity. So this filter is telling you how this ganglion cell spatiotemporally summates photoreceptor inputs. For example, this ganglion cell likes a depression of light here and an excitation of light in the surround, right? And then you rectify it. Okay, so it's a very basic setting. So if you compute these spatiotemporal filters for the primate retina, you find that the primate retina has multiple cell types, or in the language of machine learning, the primate retina is a convolutional neural network with multiple convolutional channels. So basically, right, these ganglion cells tile space, and there's multiple types of ganglion cells, and each type tiles space, and each type has a different spatiotemporal receptive field. So what are the spatiotemporal receptive fields? Well, you get the four most dominant cell types in the primate are this on midget and off midget. Okay, so there's on and off flavors, and then there's midget and parasol. So the midget means that the receptive field in space is small, right? So it likes to summate photoreceptor inputs over a small region. And then it comes with both an off and an on flavor. So this likes a depression of light, this likes an enhancement of light. And then there's a parasols that summate over a much larger region of space, okay? And they come in on and off flavors. Okay, there's also temporal receptive field that goes with the, so this is how the system integrates in time, how each cell type integrates in time, and some are fast and some are slow. And this is the Fourier spectrum of the corresponding spatial temporal filter. Okay, so just to by the way, this is part of a bigger effort in experimental neuroscience, which is that the brain is comprised of many, many different cell types, right? However, and there's a lot of, the advent of single cell RNA sequencing and so forth, the technology is now there to measure genetically defined cell types, right? But the theory needs to catch up. There's no theory for why we have so many cell types. So this is going to be a big open question in neuroscience. And so we attempt to address this question in the retina. Okay. All right, so just to summarize, okay, the midget cells have a small spatial receptive field and they turn out to have slow temporal filtering. The parasol cells have a large temporal receptive field and they turn out to have fast temporal filtering. The midget cells, there's lots of them. There's very few parasol cells. And then the midget cells are very sensitive. The parasol cells are not very sensitive. The parasol cells are highly sensitive. They have a high gain. Okay, so a critical question as a physicist that you'd really like to understand is why is space and time intertwined in this fashion in the retina? Why are the cells that are small in space slow in time, and why are the cells that are large in space fast in time? Okay, so we set out to address this. So what we did, so the way that we did it, the way that we analyzed this was we asked, or tried to explain this was we asked, what if you had an optimal retina? How would that optimal retina behave if you allocated it more and more cell types or equivalently convolutional channels? So the idea is we take natural movies and we feed them into a model retina, okay? That maybe this one only has one cell type, this green cell type. And so each cell type has a spatial temporal filter that's copied across space. So it's a convolutional neural network. And then we ask, depending on how you choose this filter, how well can we linearly reconstruct the natural movie, assuming there's some noise and a constant firing rate budget? We compare that to a convolutional neural network with multiple cell types. And we do an apples to apples comparison. We allow the neural network with two cell types to only have the same number of neurons as a neural network with one cell type. And we also equalize the overall firing rate for each of these cells. So we have a constant firing rate budget. So then what we do is we optimize the filters for one cell type versus two cell types, subject to an overall firing rate budget and an overall number constraint on the number of cells. And then we ask, does a multiple cell type network do better than a single cell type network? And it does. And the question is why? Okay, it's critical that we optimize the system for natural movies, the very movies that sculpted the evolution of the retina. Okay, so what does the power spectrum of natural movies look like? Okay, this is the space-time power spectrum of natural movies. It has a power law structure, all right? And basically there's these two tails. There's one tail that has lots of power at high spatial frequency and low temporal frequency, and another tail that has power at low temporal frequency, low spatial frequency and high temporal frequency. Okay, the reason that a two cell type model does better than a one cell type model is that the filters specialize to different regions of the power spectrum of natural movies. So with one cell type, the power spectrum of this filter better cover as well as possible the power spectrum of natural movies. But you can do better if you have, for example, two filters. One will concentrate here and the other will concentrate here. Okay, so let's discuss, and by the way, for a linear retina model, we can analytically compute the optimal filters. And this is what we find. I'll just give you the qualitative answer. So the filter that specializes to having its power spectrum support in this region of the power spectrum of natural movies, right, necessarily has high spatial frequency. So in the space domain, the filter is very tiny, right? It therefore has to focus on low temporal frequency, so it's a slow integrator, right? It also has to tile space. So if the spatial receptive field or filter width is tiny, you need many, many cells to tile space. And because you have lots of cells, in order to not bust your firing rate budget, they cannot fire very much. So they have to have a low firing rate and not be that sensitive to inputs. This exactly has the property of midget cells. Okay. The second cell type, which focuses its filter on this region of the power spectrum of natural movies, has low spatial frequency, right, over here. So its spatial receptive field in space is wide. Because it's focusing here, it has to focus on high temporal frequencies. Okay. And because it has wide receptive fields, it doesn't need that many cells to tile space. And because there aren't that many cells, they can fire more without busting your firing rate budget. Okay, so we can show all of this analytically, and there's mathematical formulas for all of this for a linear network, for a linear retina model. Then what we can do is we can add the rectification and solve the problem numerically for a nonlinear retina model. And this is what we find. Okay, remember, this was the data that I showed you from a colleague of mine at Stanford, E.J. Chichilinsky's lab. These are 4 cell types in the primate retina. Their spatial receptive field and the temporal receptive field. These are the optimal cell types that we get from our model nonlinear retina when we have 4 cell types. And when you add 4 cell types, you get the on and the off flavors. And there's a very nice match between what's optimal for natural movies and what evolution actually found. Okay. And there's more quantitative comparisons we make in the paper. But so just to summarize, what we show is that if we optimize neural networks to be optimal convolutional autoencoders of natural movies, out pops the detailed structure of the primate retina up to the 4 most dominant cell types. You might ask, oh, by the way, the 4 most dominant cell types capture about 50 to 60% of the cell types. You could ask, what's the 5th most dominant cell type? It's sensitive to color. And we did the optimization for black and white movies. If you redo the optimization for color movies, out pops the 5th most dominant cell type, which gets you about 75% of the cell types. Okay, so so now I'm going to shift to a completely different module, and we're going to discuss more physics next. Okay, so this is about quantum neuromorphic computing with atoms and photons. Okay, so the next thing I'm going to talk about is actually unpublished. We started a review article. We finished a review article here. And then there's a second part of this, which is actually published. Okay, but I'm going to start with the unpublished stuff. Okay, so my colleagues at Stanford and also NTT Research, they were able to build a quantum optimizer from interacting photons. Okay, so I won't go into the details of the physics of the machine because we can come up with a classical model of it that's relatively easy to understand without the physics. But just very quickly, what they have is that they have a system of interacting photons that interact with each other by traveling through a waveguide and interacting with various nonlinear crystals and so forth, such that effectively the photon polarization states with these nonlinear interactions become roughly binary variables, and they can interact with each other through quadratic interactions. Okay, you can find much more details about the physics of the machine, for example, in this review article that we wrote. By the way, the analysis of this machine is joint work with a grad student, a very talented grad student, Atsushi Yamamura, and my colleague Hideo Mabuchi in the Applied Physics Department at Stanford. Okay, so what is this machine good for? It's good for optimization. So let's talk about just a classical conceptual model for this machine. So first, let's talk about just the Icing energy model, right? So this is an energy function where it's an energy function over a set of binary variables, okay, with a particular choice of JIJs. It could be an arbitrary set of JIJs. And this is an interesting energy function because a lot of problems of combinatorial optimization can be encoded as an Icing model energy minimization problem for some value of the JIJs. So you can think of the JIJs as encoding a particular combinatorial optimization problem. Okay, for example, max cut can be encoded this way, and so forth. Okay, so this is a problem that computer scientists and optimization people would love to solve. Okay, it can be a very hard problem because it's a combinatorial optimization problem if the xi's are plus minus 1. Okay. On the other hand, we could try a relaxation of this problem. If we relax this problem so the xi's are not constrained to be plus or minus 1, the xi's are real numbers subject to an overall norm constraint, then minimizing this problem over this larger domain is a very simple problem. its solution, the solution to this energy minimization problem is just the eigenvector of J of maximal eigenvalue, right? Now, of course, we could round this maximal eigenvector and get an ansatz for the solution to this original problem, right? i.e. compute the maximal eigenvector of J and just take the sign of each component of the maximal eigenvector. And then you get a feasible point in this optimization problem, but it may not have good low energy from this perspective, okay? So this coherent Icing machine, what you can effectively think of it as doing is you still have a bunch of soft spins that are real valued numbers. Basically, these real numbers come from the X quadrature of an optical parametric oscillator populated by a photon electromagnetic field. And then you have multiple optimal parametric oscillators that are interacting. So each Xi comes from a photon state, okay? And they're interacting. If you think about the individual optical parametric oscillator, it has this single site term, right? Where this A is roughly related to the laser pump power that you use to power these optical parametric oscillators, right? If the pump power is negative, right, then this is a convex function. So the single site Hamiltonian looks like a convex function. Oops. But if you start pumping laser power into the system, this term will become negative, right? For positive A, this term will become negative. And the energy function for a single photon or mode of the electromagnetic field will become like a double well potential until A becomes so large, these double wells will become so deep that this will be forced to be a binary spin type variable. So it'll come back to up here. But then you also have this interaction function, and this machine is powerful enough that you can program arbitrary JIJs. You can encode arbitrary combinatorial optimization problems if they can be encoded as an Icing system. Okay, so what's happening is this machine is continuously interpolating between the spectral relaxation for large negative A and the Icing system for large positive A. And the question is, can we do better in finding solutions to this Icing problem, which we care about, by annealing from low laser power to high laser power? That's the question we'd like to ask. Okay. We're going to ask it for a very specific set, a very generic set of JIJs, where we're just going to take the JIJs to be drawn as IID Gaussian with zero mean and variance 1 over n. So this is the classic Sherrington-Kirkpatrick spin glass. So what we're going to be doing is we're going to be analyzing how well the coherent Icing machine can solve the Sherrington-Kirkpatrick spin glass. And what we find empirically is that it does it remarkably well. So if you do this deterministic annealing, where you start at low laser power and you slowly increase the power. So you basically start from low laser power, you increase the power a little bit, and then you minimize the energy via gradient descent, and then you repeat, okay? And these are the Icing energies that we find through numerical simulations at various system sizes. The ground state energy density, or energy per spin, of the SK model is known. It's about minus 0.76, okay? The energy obtained from eigenvector rounding, i.e. the spectral relaxation, is up here, okay? And this is what we find by deterministic annealing, right? And there's some finite size scaling where smaller problems have slightly higher energy, and that's a property of the SK model. So we're doing much better than spectral relaxation. And so now the question is why? What makes this possible? What is the shape of this energy landscape? How does it change with laser pump power? And moreover, how can we exploit our understanding of this changing geometry of the energy landscape to determine this optimal annealing schedule, which I'm showing you? These are the results of the optimal annealing schedule that we used. Okay, so that's where we're going. So this requires sort of a bit of a review of the geometry of high-dimensional error landscapes, but here's a basic idea. Consider a different problem, for example, a random Gaussian error landscape over n variables. Okay, let's let X be a critical point, a place where the gradient vanishes. Let's let E be its error level, and let's let F be the fraction of negative curvature directions of the Hessian, the second order approximation to the critical point. Okay, you might think that critical points would live anywhere in this landscape, but they actually don't. For this particular problem, they concentrate on a monotonically increasing curve. The global maximum is here. It has the highest error or energy, and the fraction of negative eigenvalues is 1. And as you go down lower and lower, what happens is you develop more and more negative curvature directions until you get to near the bottom, and then the most likely typical minimum will exist at a certain energy level. So if you randomly pick a typical minimum, you'll get this energy level, and the global minimum's energy might be a little bit lower. Okay, that's what happens, for example, in random Gaussian landscapes. So basically, local minima at very, very high error are exponentially rare in the dimensionality of the problem. Okay. So we wanted to understand this for this. Oh, and by the way, this is old work that we did, in this paper. We showed that this property of local minima at high error being rare is also true for machine learning problems of interest. And so, if you're interested in these details, you can see them in this relatively old paper. Okay, but we wanted to understand this quantitatively for this coherent Icing machine. So the questions we asked are, in terms of the CIM energy, the radial distance from the origin, and the laser pump power, where does the global minimum lie? Where do the local minima lie? Where do the most likely saddle points of a given index lie, where index is the number of negative curvature directions in the Hessian, or negative eigenvalues in the Hessian? Where do the lowest energy saddle points of a given index lie? And given a critical point, what is the distribution of the optical parametric oscillator quadrature amplitude? Okay. And what is the eigenvalue spectrum of the Hessian of a critical point as a function of its index, energy, and radius? Before I tell you the answer, before I go through the results that yield the answer, I want to just give you a conceptual picture of the answer. What we find is that at high laser power, at large A, when you have many, many local minima, what happens is the structure of the energy landscape looks like this. So this vertical axis is energy. These two horizontal axes are a stand-in for the n-dimensional space of the x's, right? And what you find is that at large A, you get this hierarchical structure where high index saddle points with lots of negative curvature directions occur at high energy and small radius. And then as you go further and further out in radius and lower energy, you get lower and lower index saddles until you get a wall of typical local minima here at large radius. Right? And then the global minimum can occur, a very large A can occur at a slightly lower energy and even larger radius. So if you were to not anneal, if you just started at large A and started optimizing, your optimization trajectory would go down and down in energy, larger and larger in radius, and it would get stuck near this wall of typical local minimum. Okay, that's what will happen. On the other hand, if you anneal and crank up A, what happens is this picture kind of inflates and expands. So you can start beyond the wall of typical local minima at large A and adiabatically follow them. And that's the secret of success of annealing. So I've basically given you the take-home message. Now let me give you the justification for it. Okay. So but what are the theoretical techniques? So we can analytically compute a lot of these quantities. The theoretical techniques that we use are, we again use ideas from the system mechanics of sequential disorder. We compute the number of critical points at a given energy and radius and index. We use the Catch-Rice formula to compute it. We use the replica method to carry through the calculation, and we have to deal with determinants of some matrices. So we put in fermions to deal with the determinants. And then we have to, and there's a supersymmetry in this calculation, so we often have to break the supersymmetry. Again, these are all a lot of technical details, which I'll spare you, but that's the basic idea, okay? These are some of the results, okay? So this is justifying this picture now. Let's, for example, take a large value of A. What I'm showing you is, as a function of energy in the horizontal axis and squared radius, i.e. sum over Ixi squared on the vertical axis, the heat map is the numerical density, a logarithm of the numerical density of critical points we find at a given energy and radius. Okay, the black points are the average energy and radius of critical points of a given index, the mean. Okay, so this is low index out here. It occurs at low energy and high radius and large radius, and this is high index. The red curve is our theoretically computed location of these averages. And you can see there's a really nice match. So this is justifying this picture that high index critical points with many negative curvature directions occur at high energy and low radius. And as you go further out and down in energy, you get to the local minima out here. Okay. Of course, we care even more about the local minimum and the global minimum, right? So we were able to compute for a typical, so for example, if you find a local minimum of this Hamiltonian, you could be interested in, for example, the empirical histogram of the xi's at the local minimum or the global minimum, and also the Hessian eigenspectrum at the local minimum or the global minimum. Okay. And what we find here is that empirically, this is the distribution, this orange curve. Sorry. The blue histograms are the empirically derived histograms for the Hessian eigenspectrum and the histogram of xi from brute force search over problems of size n equals 20 to 40 or so. The orange curves are theoretically derived curves, and there's a nice match between theory and experiment. You can see as you crank up the laser power, the photons or the spins commit more strongly to a plus or minus one value, a positive or negative value. The Hessian actually has a spectrum that extends all the way to the origin. So there's many, many flat directions in the landscape around typical local minima. Okay, so the landscape around typical local minima is quite flat. The global minimum is very different. Of course, at low laser power, it's quite flat. The spectrum extends to 0. Of course, the spins commit as you increase the pump power, the laser pump power. But there's a phase transition where the Hessian eigenspectrum achieves a gap, where there's a gap between 0 and the lowest non-zero value. So now the global minimum has no flat directions, it's sharp. So that's like a freezing transition. And I realize I'm running out of time, so I'm just going to give you the final take-home message for the phase diagram. There's a sequence of geometric phase transitions in the geometry of the CIM energy landscape. There's a so-called replica symmetric phase where there's sort of this laser pump parameter is negative, and it's just a convex single well. You crank up the power, so you're making the photons try to commit, and then you get exponentially many local minima, but they all have the same energy and they're very, very flat. Okay. Then there's a SUSY breaking phase transition, right, which happens at a larger A, where you still have exponentially many local minima. They're still quite flat, but now there's a gap between the energy of the global minimum and the energy of a typical local minimum, right? So there's this energy gap. The global minimum still is flat. The Hessian spectrum extends to 0. Then finally, there's a freezing transition where the Hessian spectrum of the global minimum is sharp. There's a gap in the energy spectrum. And because we understood all of this, we found that the optimal thing to do is to anneal as slowly as possible until you get to this freezing transition and then stop. And so without going into the details of that, this is exactly what we find. When we look at the Icing energy that we find, if we anneal up to a certain laser pump power, we find that the Icing energy goes down as we anneal up to a larger and larger laser pump power. This black curve is the limit of very slow annealing. We do better and better if we anneal up to a particular laser pump power, but our performance stops once we get to here. It stops at a very good value. And if we anneal faster, we do worse. Okay, so basically the performance of this deterministic annealing procedure can be characterized by the phase transition, the geometry of the landscape. And this is, by the way, this is the performance of annealing, right? This is the laser pump power, and this is the energy of the state found by deterministic annealing. It follows pretty closely the energy of the global minimum, and it goes below the energy of the typical local minima. So that's what I was saying. Deterministic annealing is like surfing this inflating onion and staying always beyond the edge of the local minima at any value of A. Therefore, you don't have to solve the hard problem of rapid quench starting from large A. Okay, and I'll stop there. What I didn't cover was storing memories in a cavity QD system like a Hopfield model, but that's actually published work that you can check out. So let me just end with the references, and I can take questions now. Thanks.
Thank you so much, Surya, for a fantastic talk there. That was quite a tour de force. First warming up by optimally doing high-dimensional regression, then figuring out why evolution built the retina the way it did, and then ending off there by showing how you can take an NP-hard problem and in practice actually solve it.
I wouldn't go so far in the last part.
Almost perfectly.
Yeah.
And we have a lot of questions that have accumulated in the chat here. So let's start with the first of your three vignettes here on the high-dimensional regression business. So we first have a question from Shantan Singh, who wonders, you mentioned there that you have an exact solution for these two cases. And in one case, it's a Gaussian, so the log of that logarithm is just a parabola, and the other case, it's an absolute value function. And Shantan is wondering if you had any explicit expressions in between there. Is it maybe other power than one or two, or
yeah,
what?
Sorry, I neglected to mention, we have explicit expressions for the entire spectrum, and the expression involves a nonlinear convolution. So you convolve in a log domain, then take an exponential, and that's how you get. So basically, we have an algorithmic procedure. We have an analytic formula that gives an algorithmic procedure for computing the optimal loss function at any measurement density.
Amazing. And then we have two questions from Sona Najafi and Alex Maloney, both involving replica tricks. So Sonia wonders if it says that usually with a quench disorder, you need the replica trick for the averaging, and wonders if you use a similar one. And Alex wonders regarding the replica trick, what happens if the probability distribution is such that replica symmetry breaking is allowed? Is there something like the Parisi ansatz at low temperature and a phase transition as the probability distribution becomes non-log convex?
Yes. Yes, we use a replica trick both in the first part and the third part. In the first part, we stuck with replica symmetry breaking. We stuck with replica symmetric. And that was the origin of our technical constraint that we need log concave signal and noise. You can go to replica symmetry breaking if you don't have that. People have done that, for example, for compressed sensing, where you have sparse distributions that are not log concave. And then you have to go to full replica symmetry breaking. And then for the third part, we actually did full replica symmetry breaking. So it's because as you crank up the laser pump power, the energy landscape becomes more and more like that of an SK model. And it's well known that the SK model's low temperature physics is only described accurately by full replica symmetry breaking. So we had to do that. So as far as I know, in the literature on looking at the geometry of continuous energy landscapes, I don't think anybody has worked out the geometry of an energy landscape that requires full replica symmetry breaking, but I could be wrong. A lot of people look at like the energy landscape of tensor completion and so forth, where one-step RSB is good enough. One-step replica breaking is good enough.
Sona, I see you have your hand up there. Did you have a follow-up question?
Yeah, maybe. Now that you mentioned, so I think that you partially mentioned it, but like I was wondering. So, for example, for the replica method to work, also in the last part of your talk, you mentioned you consider showing Patrick that you have actually this full connectivity. How that is related with the structure of the data or the underlying machine learning problem that you were looking at?
Yeah, so the first part was about machine learning. The third part was really about optimization. Like you just have an optimization problem that you want to solve. So for example, there's a whole review articles on how you take various combinatorial optimization problems over binary variables, and you can rewrite them as energy minimization over an Icing system for a particular choice of JIJ. And there's whole articles about how, for specific optimization problems, how you encode the optimization problem as a JIJ. We were looking at a specific problem, the SK model. We weren't looking at other problems like max cut or number partitioning. So there could be an entire industry of working out the energy landscape for various problems, which we've only just started. We're going to look at some of the other ones. There's some interesting MIMO optimization problems that we're going to look at next that are like the Hopfield model.
Yeah, can I then maybe that now that you answered that part too. So I was also, for the last part of your talk, if I understood correctly, is that this is actually the experiment built on the quantum system, the photonic system that we have. Then the first question I had, like, what is the quantumness playing the role in this problem compared to the classical one? Because I think that's like a very important question. And the follow-up also I think that you briefly mentioned as well. So for example, now in your optimization problem, that you mapping optimization problem to this spin model, which is like known, how this is compared to also quantum optimization algorithm. For example, QAOA, for example, that's like, for example, is state of art for the quantum optimization.
It's a great question. So my colleagues like Yoshi Yamamoto are doing a whole bunch of benchmarking with the coherent Icing machine and the QAOA and things like that. I haven't worked on that kind of stuff, but for various problems, one outperforms the other or vice versa or something like that. So we analyzed, in this talk, we analyzed the classical limit of this photonic machine. We're interested in analyzing by changing the parameters, you can make it more or less quantum. We're interested in understanding the more quantum aspects of it. But then the problem becomes our ability to simulate the system or measure the system in this quantum regime. And so we're actually looking at a different regime where we're looking at maybe 4 photons or something like that, and asking for these low dimensional problems, what quantum effects can help in optimization. And so this is a collaboration that Hideo is working on as well. And I think there's a major open question, which is, how does quantum dynamics negotiate high dimensional landscapes that are riddled with saddles? I think nobody has good answers to that, including ourselves, right? But that's a major open problem. We're trying to engineer interesting 4-dimensional landscapes in which there's a qualitative difference between the quantum dynamics and the classical dynamics. That's where we're at the moment.
Perfect.
Before we talk more about this one, we have a bunch of questions also about, 2 at least, have come in about the second vignette, how the retina works. That both are evolution related. Moshir Harsh is wondering about if evolution has made these 4 types of retinal cells more or less the same across lots of higher organisms, if you comment on that. And on YouTube, Aman Sinya is wondering about also how conserved this 2-dimensional spatio-temporary power spectrum is really. Is it always like that for all movies? Or are there other environments that maybe other species just find themselves in where it's very different?
Oh yeah, it's a good question. So first of all, these retinas are not universal. So for example, prey and predators have very different retinas. For example, a rabbit, 40% of its cells are devoted to detecting overhead predators, overhead motion. So the design principles of the rabbit retina are completely different from the design principles of primate retina, where the primate is a predator. So there are these major design principles. So it's thought, roughly speaking, what happened in evolution is that the retina was a very specialized system to detect very behaviorally relevant things for the animal. But then as the animal got smarter and smarter with a bigger and bigger brain, the retina became a general purpose, camera in some sense, much more sophisticated than our current cameras because they can adapt to different light levels and stuff. So as far as we know, in most mammals that are predators, it's a very similar structure. Of course, like retinas of fish adapt to different indexes of refraction and so forth, and light levels in the deep and so forth. So we haven't done a full survey, phylogenetic survey of this.
You touched on it already, but maybe you can say a little bit more also about Arnav Tripathi's question, which is why 4? Why wouldn't we expect to see even more cell types to really specialize in all the different parts of the K versus omega space?
Yeah, there's an issue of diminishing returns that we see. So we see a lot of diminishing returns. But having said that, the primate retina has about 20 cell types. Okay, so biologists are notoriously contentious about how many cell types there are. There's a lumper versus splitter debate. But a rough consensus is about 20 cell types. And some of the cell types are really weird. Some are specialized to detecting motion, right? Some are specialized to detecting sort of local versus global motion, right? Like if your head moves from left to right, the entire world moves in your retina. but we don't have a percept. We don't think the world is moving. We know our head is moving. That problem starts to be solved in the retina, where you have cells that can detect only differential motion of the center versus surround. So there's all this weird stuff in the retina. So there might still be specialized circuitry even in the primate retina, but like the top 70% of the cell types can be explained through very general purpose reasoning.
Fascinating. And coming back to the third part here, the Icing solver, you were very modest there and said, I haven't solved anything or nearly solved anything NP hard, but it's pretty intriguing that you're finding quite good solutions. And if you're not getting the exact one, you're getting very close. What's the largest N that you have been able to build this for? You talked about N of 20 and I think 40.
Oh, yeah. Yeah, so NTT, Yoshi Yamamoto, who used to be at Stanford, had moved to NTT Research, and actually now that we're collaborating with them, they can build stuff. I don't even know the latest numbers, but I've heard stuff like around 4,000, 5,000, something like that. So yeah, I mean, this is not. I don't think it's going to change the exponential scaling, like of solution time with problem size, but I think it yields a very interesting intellectual landscape to understand how optimization dynamics depends on geometry, and moreover, how quantum mechanics might play a role in modifying the classical dynamics. So I'm in it for the intellectual interest rather than thinking I'm going to make money off of this someday.
Well, I'm still trying to understand your modesty here, because in practice, if you want to make money off of things, people don't usually care if it's the exact optimum. If it's 99.9% there in terms of performance, so who cares? Yeah. So if you just want something really good as a solution to the traveling salesman problem or any of these Icing encodable ones, why don't you actually beat the exponential scaling? Or what are we missing?
Yeah, so that's actually an interesting question, right? Like, you can ask, how long does it take me to get within epsilon of the ground state, right? Now, if epsilon itself scales maybe sublinearly with n, right, or sublinear is 1 over n, then maybe you don't need exponential time to get like a bad solution, or bad is still pretty good, right? So I think this notion of NP hard developed by, this notion of NP hard developed by computer scientists just means that in this class of problems, there's at least one problem that's very, very hard. But for generic problems that show up, that we actually care about, they often have more structure. They're often quite feasible to solve in ways that we don't understand. Like, we don't have very good theories of average case complexity and an understanding of natural problem distributions, right? So I suspect actually, yeah, maybe to make money, you don't have to solve NP hard problems, right? That's completely irrelevant. So yeah, what's the conclusion?
Yeah, I mean, that reminds me of what Professor Bart Selman at Cornell likes to say. He spent much of his life as a computer scientist studying NP hard problems, which finds that the typical instantiation of a problem is usually way easier than the worst case one.
Exactly.
And in industry and in science, we often don't care about the worst case one anyway. So is this the thing you built, actually the best Icing solver out there? Or
there are multiple Icing solvers out there. Andrea Montanari, for example, has a message passing algorithm to solve the Icing problem that can get to within epsilon of the ground state provably with some constant factors that remain unspecified. So I honestly don't know if it's the best one out there. Like, I mean, there's various performance criteria depending on how, best for what degree of, I mean, there's accuracy speed trade-offs. So there's going to be some Pareto optimal frontier of Icing solvers. And I don't have a good sense of where on that Pareto optimal frontier this one sits. Right. It works pretty fast if you want to get to minus 0.75 energy density, where the ground state is minus 0.76, right? So that's where we're at, basically.
All right. Now, Richard Charette, you have a question here containing the word aves, which is a word I don't know.
Birds.
Maybe you mean waves.
Birds.
Huh?
I was talking about birds, like raptors, penguins, and so forth. Like, how do their eyes work in terms of this? Because different birds have different food sources, and they have predators or prey. So I was wondering about that aspect.
Yeah, it's a great question. To be honest with you, I've never studied the retina of birds, so I don't know. There is, there's a big difference again between predator and prey, where like predator birds will have their eyes in the front, right? And birds that are often preyed upon will have their eyes on the side. Makes sense, right? Because you can easily look back. So I suspect there's specialization in the positioning of the retina on the body, and I'm sure there's different spectral sensitivities in terms of which colors they're sensitive to or whatnot, depending on what kind of prey and flowers they like and so forth. So I'm sure there's specializations there.
Cool. Let's open it up here. If you have more questions, you can just put your hand up. I'll call you out. I think you, Sona, had another question. I saw you put your hand up again.
I didn't, but I think that I have just like maybe like a comment as well. I think it's just not also like targeting the solving some problem. I think what is also probably more interesting about the quantum part of this kind of like problem is that if we can actually understand the learning and what quantumness would add to this sort of learning procedure. We're actually looking at now currently at Harvard with using a neutral atom and looking at some of this learning algorithm, like similar questions that can we actually get any advantage from the quantumness, and can we actually understand what is happening during this learning process? I mean, if we solve an NPR problem, of course, in the end, that would be also.
I mean, one of the dreams is that like if there are multiple pathways to the minimum, could you somehow get constructive interference between the pathways, right? That would be one dream. It remains to be seen whether that's what happens in this machine. I mean, actually, I can turn it around. Like, do you see any particular advantage of quantum versus classical in an optimization?
Yeah.
Oh, so what is it?
I mean, in our system,
what's the conceptual advantage? Like the conceptual.
I think it's more toward the again, like what we can describe with the probability distribution that we can get from a quantum system compared to the classical one. But I don't think that, I mean, we have one paper coming up pretty soon and some like follow-up papers, but I'm interested just looking at different quantum system as well, right? The one that you showed for photonic system, maybe that is good for some of the tasks compared to the neutral atoms and compared to other quantum systems that are out there. I think it's just like wide open, field to actually look at.
Oh, that's much better. I can see all of you.
Since you asked us the question here now about whether there's some conceptual reason to think quantum outperform classical for optimization, do you think that quantum tunneling could be such a thing where you can tunnel out of a local minimum you'd otherwise be stuck in classically?
It could be. I mean, the question there would be, is it specifically any better than thermal hopping, right? There's various like quantum noise formulations of these OPOs and all that. And what I'm not an expert on the quantum dynamics of OPOs, but I keep asking my experimental colleagues, like, okay, so is there some property of the quantum noise that's fundamentally different than the thermal noise that helps in optimization? And I've never gotten a clear answer so far. So it would be interesting to find I think what we need is we don't need to look at very large problems. We need to find a single toy example where there's a qualitative difference between quantum noise and thermal noise, right? And I honestly haven't seen that example yet. Of course, that doesn't mean it doesn't exist because I'm not an expert in this field. But I'm sure there's experts on this call. So if you've seen one, do speak up. I'd love to hear it.
Fascinating. How long time does it take for your laser-powered quantum your laser-powered Icing solver to actually do the annealing? You said a very long time. Are we talking seconds or minutes?
So all of the results that I shown you were done in silico on a simulator of the machine. So basically what happens is your annealing schedule has to be slower than the flat directions in the local minima, right? So you need the system to settle before you crank up the laser power again. In terms of clock time, I mean, these things are super fast in terms of clock time. I mean, sub-second, right, is what they operate at, especially at like size n equals 4,000 or something like that. So I've never actually used the physical machine, but I'm guessing it would be definitely sub-second to reproduce the simulations that I showed you on the screen.
But the 4,000, the n equals 5,000 machine that you mentioned, is it built actually with a laser, or was that a simulation of it?
Well, that one's a hardware implementation.
Okay.
Yeah, done at NTT.
Amazing.
Yeah.
Any more questions for Surya? At this point, you can just shout out. Right. Any more questions from you, Surya, to us?
No, I'd
Kind of
love
a
to
great
hang
one.
out with all of you and learn from you. I mean, it'd be fun.
Yeah.
When this whole
Well,
pandemic thing is over, it'd be great to visit and hang out. Yeah,
Yeah,
congratulations on the NSF Center. It's very exciting. I'm glad there's a physics and AI NSF Center. That's fantastic.
So we are so delighted that you could come and visit us here. So to take a rain check on coming and visiting us whenever you feel the time is right. I know you have an inbound stork arriving pretty soon, so it's
Oh yes,
probably
in a month.
probably won't let you come visit us within the next month, right?
No. For next month, you're optimistic. I mean, probably for a few more months after that.
Exactly.
Yeah.
Exactly. But on behalf of all of us, thank you so much again. And let's all show our appreciation for Surya for coming and visiting us here. And